Welcome to the deep dive. Today we're jumping into Seed 1.5-VL. It's a really cutting-edge vision language model that came out of a recent research paper.
Yeah, it's a fascinating one.
So think of this as your technical shortcut. We want to help you understand the innovations behind these models that can, see, read, and actually reason about images and even video.
Exactly. The paper really lifts the lid. We get to see the architecture, the sheer amount of data involved. There's specific training methods which are quite unique.
And the infrastructure, right? There's stuff needed to actually build this at scale.
Absolutely. Huge compute.
So our mission today, we're going to unpack the key technical breakthroughs. What really makes Seed 1.5-VL stand out. We're not just listing features. We want you to grasp why these specific choices are pushing the envelope in multimodal AI.
Couldn't have said it better. Let's maybe kick things off with the basic structure, the building blocks.
Okay.
So, like a lot of VLMs, Seed 1.5-VL has three core components. You've got a vision encoder that's for processing the images,
Right.
an MLP adapter, which kind of acts as a bridge between the vision and language parts.
The translator.
Sort of, yeah. And then a large language model, the LLM, which handles the text side, the reasoning, generation, all that complex stuff. But the interesting part is really how they put these pieces together, especially the vision side.
Okay, so what's innovative about their vision encoder?
Well, a really key thing is how it deals with image resolution. You know how most models make you resize everything to a fixed size?
Yeah, like 224 by 224. They can lose detail.
Exactly. It can lose detail or introduce weird artifacts. Seed 1.5-VL's encoder supports dynamic image resolutions natively.
So you can feed it a tiny image or a massive one, and it just adapts. No forced resizing.
Pretty much. And the way they achieve this is using something called 2D rotational positional embeddings, or 2D rope.
Okay, ropey. I know that from LLMs, but 2D.
Right, so think of positional embeddings as giving the model a sense of where things are in the image. Standard methods often lock this location sense to a fixed grid. 2D rope is different. It lets the model understand spatial relationships in a way that scales with the image size. Much more flexible.
That makes sense.
And for those really high-res images, they also have an efficient pooling step. It compresses the visual features before they hit the big LLM, keeping things manageable computationally.
Smart processing, not just brute force resizing. Okay, how do they actually train this vision encoder part of the seed vet?
It had its own dedicated pre-training pipeline, kind of a multi-stage thing guided by specific goals. First up was masked image modeling, MIM, but using their 2D rope.
So like hiding parts of the image, making it guess.
Yep. And doing it with 2D rope helps it build a really robust understanding of visual structure, geometry, how things relate spatially, regardless of the scale it might see later.
Like teaching it the visual grammar before showing it full pictures.
Exactly. A good analogy. Then, stage two for the vision part was native resolution contrastive learning. This is more about connecting the visuals at their true resolution with text descriptions.
Okay, linking the what it looks like to the what it means.
Precisely. Getting that visual semantic alignment right at the source resolution. These steps are really foundational before you throw the full multimodal complexity at it.
Right. And speaking of complexity, data, that's always a huge part of these models. What did their data diet look like?
Oh, it's massive and incredibly diverse. They start with the usual suspects, huge amounts of unlabeled images, image text pairs scraped from the web, that kind of thing.
Standard stuff.
Standard base, yeah. But where they really innovated was in curating specific, challenging data sets. These are designed to teach the model very targeted skills, going way beyond simple image captioning.
Okay, like what? Give us some examples.
All right, so one big area was STEM problems. Science, tech, engineering, math. They pulled together over 1 million examples.
1 million. Wow.
Yeah. And it's not just text problems. It's about understanding images within STEM contexts, diagrams, charts, synthesized tables, visual math problems, for P12 stuff right up to adult education level.
So it learns to actually interpret a circuit diagram, not just describe the lines.
Exactly. Understand the concepts visually. Then there's GUI data, graphical user interfaces.
Ah, like websites and apps.
Yep, pulled from sources like UITARs. This data is all about robust perception and reasoning for interacting with software visually. It includes screenshots paired with structured info about the elements, buttons, menus, text fields, and tasks like describe this button or caption all the interactive elements or even understanding the sequence of actions for a task.
Teaching it to use a computer visually. That sounds incredibly useful for applications.
Huge potential, yeah. They also put a massive effort into chart data. Over 100 million examples here.
100 million charts. How?
This is where their data generation pipeline comes in. They mixed existing chart datasets with a novel method using LLMs to synthesize new charts.
Wait, using an AI to make training data for another AI?
Kind of, yeah. One LLM might generate the underlying data in text for, say, a bar chart. Another part translates that into code to actually draw the chart. Then it gets rendered as an image. It's a really scalable way to create diverse chart data.
That's quite clever. And efficient, I bet. What else?
Finally, video data. They structured this carefully to teach temporal understanding. Not just captioning a whole video, but things like proactive reasoning, where the model has to respond almost frame by frame to what's happening.
Like live commentary?
Sort of, yeah. And actual real-time commentary data, too, for really fine-grained alignment between the video action and the text description. It's about understanding sequence, timing, cause and effect in motion.
That's a seriously comprehensive data strategy. But you mentioned distribution challenges earlier. Even with all this data,
Yes, absolutely critical point. Raw web data, especially image-text pairs, suffers heavily from the long tail problem.
meaning you see cat and dog millions of times, but rare stuff hardly ever.
Exactly. You see common concepts constantly, but rare species, specific tools, niche scenarios, they barely appear. If you just train on raw frequency, the model gets really good at cats and dogs, but terrible at anything uncommon. It becomes biased.
Right, it overfits to the common stuff.
Precisely. They showed this clearly using the Biotrove dataset. It's full of diverse species. Training on a massive but skewed dataset resulted in poor performance on the rare species. But then they tried simple balancing strategies,
Like what?
like just capping the number of examples per common category, say limiting cat images to a maximum of 1,000, even 100 samples, max 1K, max 100.
And that helped.
Significantly boosted performance on the rare species. Even if it slightly dropped the score on the most common ones, it really underscores that smart data curation and balancing are just as vital as sheer volume if you want a model with truly broad understanding.
Balanced exposure is key. Okay, so they have the architecture, they have this carefully curated data. How did they actually train the VLM? What was the overall approach?
Their strategy is what they call post hoc adaptation. They don't train the whole thing from scratch. They start with strong, pre-trained components.
The vision encoder we talked about.
Right, the CVIT, the MLP adapter. And crucially, a very capable LLM that's already been trained extensively on its own, initialized from a large internal model they have.
So building on existing intelligence, not starting from zero.
Exactly. The VLM training is about teaching these powerful, pre-existing parts to work together effectively on multimodal tasks.
Makes sense. How did they structure that VLM pre-training specifically? You mentioned stages.
Yeah, they detail a three-stage process in the paper, Table 4. Stage 0 is interesting. They only train the MLP adapter. The vision encoder and the big LLM are kept frozen.
Just training the bridge?
Yep, it's like teaching that adapter how to translate the frozen visual signals into a language the frozen LLM already understands, getting the interface right first.
Like tuning the translator before letting the main experts talk directly.
That's a good way to put it. Then, stage 1, everything gets unfrozen. All model parameters, vision encoder, MLP, LLM, are now trainable, and here they use that balanced mix of all their diverse data.
Okay, now everyone learns together.
Right, this is where the model learns end-to-end multimodal capabilities. Then stage 2 builds on that. All parameters are still trainable, but they significantly crank up the sequence length.
How much information it can handle at once.
Exactly. They went from 32,000 tokens up to 131,000. That's huge. It's vital for tasks involving long videos or really complex reasoning that needs to track information over a long context. They also introduced some new data domains in this stage, like coding and 3D spatial understanding.
Longer memory for harder tasks. Did they say why this specific order of stages? Did they try other ways?
They did mention trying an alternative training the vision encoder and the MLP together first, while the LOM was still frozen.
And
They found their chosen recipe MLP first, then everything worked better.
any theories why?
Their hypothesis is interesting. They suggest that if the powerful LLM is frozen initially, the vision encoder might try too hard to compensate. It might learn visual representations that are overly tailored to the frozen LLM's limitations, potentially hurting its pure visual capabilities later on.
Ah, so it learns bad habits trying to work around the frozen LLM.
Possibly, yeah. Their method seems to encourage a cleaner division of labor, letting the vision encoder stay strong at perception while the whole system learns multimodal integration later. It's a subtle but important insight into VLM training.
Okay, let's switch gears to scaling. Training these massive models. How do scaling laws apply when you're building on pre-training parts like this? Is it different from training an LLM from scratch?
It does change the dynamics a bit. Their analysis focused on that stage 1 VLM pre-training where everything is learning together. What they found was that even within this complex multimodal training, if you look at specific subcategories of data, like all the OCR relevant data or all the visual grounding data,
Right.
The training loss for that specific skill still follows predictable power laws as you scale up the amount of that specific type of data. Figure 3 in the paper shows this nicely log-log plots loss versus data scale, pretty much a straight line.
Okay, so adding more OCR data predictably reduces the OCR-related loss during training. That makes sense.
Right. But here's the really cool part, the key finding, that training laws on a specific data subcategory, it can actually predict how well the model will perform on related downstream evaluation benchmarks.
Well, hang on. The internal training loss predicts external benchmark scores.
Yeah, apparently so. Within a certain range, anyway, they found an approximately log linear relationship. As the training loss for a skill goes down logarithmically, the performance metric on a related benchmark goes up linearly.
Give me an example.
Look at figure 3 again. The loss on OCR training data correlates strongly with performance on benchmarks like chart QA and infographic VQA tasks that need good OCR.
Okay.
And the loss on grounding data predicts performance on RefCoco, which is all about locating objects described in text.
That's incredibly useful. It means you can monitor these specific losses during training and get a good idea if the model is actually learning the skills needed for downstream tasks, potentially saving evaluation time or guiding data collection.
Exactly. It's a powerful signal. If your grounding loss isn't improving, you probably need more or better grounding data, and you know it before running expensive benchmarks. It helps diagnose what's going on inside during that huge training run.
Okay, so pre-training gets the model foundationally capable, but then they do post-training, right? Fine-tuning, reinforcement learning to make it better at following instructions and reasoning.
Yes, and this is where some of the most cutting edge stuff happens. Figure 4 gives a nice overview. It starts with supervised fine tuning, SFT.
Standard practice.
Well, yes, they use general instruction following data, but they also curated specific long chain of thought data, long COT.
Chain of thought, getting the model to show its work step by step.
Exactly. And Longcott emphasizes generating detailed, comprehensive reasoning steps. They actually generate this data using clever prompting of high quality models and then use rejection sampling to pick only the best, most thorough reasoning examples.
Ah, so they train it specifically to be good at explaining itself.
Right. And the benefit is you can then toggle this during inference, ask for a quick answer, or ask for the full detailed breakdown.
Flexible. Okay, after SFT comes RL.
Reinforcement learning from human feedback, RLHF. This involves collecting preference data showing humans two different model responses to the same multimodal prompt and asking which one is better.
Okay, standard preference tuning.
Or they have a really big innovation here. They use the VLM itself as the reward model.
Wait, the model they're trying to improve is also the judge providing the reward signal. How does that even work? Doesn't it just reward itself?
Ha, yeah, it sounds a bit circular, doesn't it? But they take an instruction-tuned VLM similar to the one being trained and fine-tune it specifically to predict human preferences. It acts as a generative classifier. Given two responses, it predicts which one a human would prefer.
Okay.
And they found this VLM-based reward model actually worked better than more traditional reward modeling approaches to handle potential biases, like always preferring the first option presented.
Professional bias, yeah.
Right. They explicitly calculate the preference probability for both orderings, response A then B and response B then A, and average them, which helps mitigate that bias. They also mention iteratively updating this reward model as they get more human feedback.
Okay, that's clever. Using the model's own powerful understanding to create a scalable reward signal with checks against bias. What was the other big RL innovation? Something about verifiable rewards.
Yes. RLVR, reinforcement learning with verifiable rewards. This is another core technique. It focuses on tasks where the answer isn't subjective, but has a single, objectively correct ground truth that can be checked automatically by code.
Ah, so no human needed for the reward signal on these tasks. That sounds scalable.
Hugely scalable. Think about visual STEM problems again. Perfect fit. They took over 1 million STEM problems, often converting multiple choice ones into open-ended questions demanding a specific answer format.
Like latex for math equations.
Exactly. The model outputs its answer in LaTeX, and then an automated verifier using the SIMPy library, a symbolic math library, checks if the final expression or numerical answer is mathematically correct based on the problem statement.
So the verifier just checks the answer, not the reasoning steps.
Correct. It verifies the final solution. They also apply this RLVR idea to other verifiable tasks, like visual grounding locating an object. The reward is simply the IOU, the intersection over union score, comparing the model's predicted bounding box to the correct one, automatically computed.
Makes sense.
Or for visual instruction following puzzles, they might use synthetic data where a simple string match or rule-based check can verify if the model followed the instruction correctly.
This seems incredibly powerful for really nailing down objective skills, math localization, following precise rules.
It really is. And they don't just use one or the other, they combine them in a hybrid RL approach.
Okay, how does that work?
The model gets trained using rewards from two sources. The VLM reward model we discussed for general, subjective, conversational prompts,
Right.
and rewards from the automatic verifiers for those objective, verifiable tasks like STEM or grounding. They even added a format reward to encourage the model to output its reasoning within specific tags like think before the final solution.
Rewarding the structure, not just the content.
Helps guide the output. They use a single critic model trained on both reward sources, normalized, and they tune the training differently, a small penalty for deviating from the base SFT model on general prompts, to keep it sane, but zero penalty on verifiable prompts, encouraging it to explore freely to find the correct verifiable answer.
Let it find the right math answer, even if it's weird reasoning.
Kind of, yeah. Interestingly, they also found that training with the long-caught data within this hybrid RL setup actually improved the quality of the model's regular non-caught responses too.
Nice side effect. Okay, there's one more piece to this post-training puzzle. It's iterative. Something about rejection sampling.
Right. The iterative update by rejection sampling fine-tuning, this is a really neat self-improvement loop. They start with their base SFT model, then they train an RL model using the hybrid approach.
Okay.
Then they take the latest RL model and have it generate responses for a set of really challenging prompts. They use their automatic verifiers from RLVR or sometimes human checks to identify which of the RL model's outputs on these hard problems are actually correct and high quality.
Finding the gens produced by the RL model on tough stuff.
Exactly. And then this is the key. They take those verified high quality outputs from the RL model on difficult prompts and add them back into the training data for the next round of supervised fine tuning, SFT.
Ah, so the base SFT model gets trained on the best verified examples generated by the more advanced RL model from the previous cycle.
Precisely. It's a feedback loop. The gains made through RL, especially on hard problems where RL might explore better, get distilled back into the more stable SFT model. The paper mentions the current model went through 4 such iterations of SFT RL generate and verify update SFT data repeat, continuous refinement.
That's a sophisticated loop. Okay, so amazing architecture, data training, all of this needs some serious hardware and clever engineering to run. What were the infrastructure innovations needed for this scale?
Yeah, this is a massive challenge, especially for VLM because they're inherently asymmetrical, right? You have this relatively small vision encoder and MLP bolted onto this enormous LLM.
Uneven workload.
Exactly. Standard distributed training methods, often designed for more uniform models like LLMs, can be really inefficient. You end up with thousands of GPUs, but some are sitting idle waiting for other parts to finish. Big waste of resources.
So typical parallelism strategies aren't ideal.
Not optimal, no. So they developed what they called novel hybrid parallelism. It's not one size fits all. They applied different parallelization strategies to different parts of the model, optimized for their characteristics.
Like what?
For the smaller vision encoder and MLP, they use something like 0D parallelism, good for distributing model states efficiently. But for the giant LLM part, they use a much more complex 4D parallelism scheme. It combines tensor parallelism, pipeline parallelism, data parallelism, and even context parallelism to break down the LLM work effectively across many GPUs.
Okay, using specialized tools for different jobs to keep everything humming along efficiently.
That's the idea. It avoids the small vision part bottlenecking the big LLM, or vice versa. They also had to tackle workload balancing specifically for the vision inputs.
Because some samples might have more images or bigger images.
Right. The computational load isn't uniform across samples. If you just send batches randomly, some GPUs get slammed while others wait. So they use a greedy algorithm. It looks at the estimated computation cost for each incoming sample and dynamically assigns it to the GPU that currently has the lowest workload.
Actively balancing the visual processing load across the GPUs.
Yep. And then there's parallelism-aware data loading. This tackles I/O bottlenecks. In large-scale parallel training, often many GPUs in a group need the same chunk of data. Loading it repeatedly from storage for each GPU is incredibly slow.
Huge bottleneck.
Massive. So their system is smart about it. It loads data only once per group of GPUs that needs it and then efficiently broadcasts it internally. And critically, they filter the data before it even moves to the GPUs. Each GPU only receives the specific image features it's actually assigned to process.
Minimizing data movement is key at that scale.
Absolutely. Keeps the compute fed without drowning in data transfer. And finally, of course, fault tolerance. When you're training for potentially millions of GPU hours, hardware failures will happen. They rely on frameworks like Megascale and techniques like Byte Checkpoint to allow the training run to be robust and recover efficiently from failures without losing days of work.
Makes sense. You need that safety net. Okay, with all this innovation, architecture, data, training, infrastructure, how does Seed 1.5-VL actually perform? How do they evaluate it?
They threw a massive evaluation suite at it, loads of existing public benchmarks covering visual reasoning, grounding, counting, video understanding, even acting as a GR agent in games.
The usual suspects.
Yes, but importantly, they also relied heavily on extensive internal benchmarks that they designed themselves.
Why build internal ones if there are so many public benchmarks already?
That's an innovation in itself, really. They argue, and it's a fair point, that many public benchmarks have limitations. A lot are very English-centric. Some are getting saturated, meaning the best models all score near perfectly, so it's hard to tell them apart.
Right, the benchmark isn't hard enough anymore.
Exactly. And some rely on simple, rule-based evaluation metrics that clever models can sometimes game, achieving a high score without truly understanding the task.
Okay, so what were the principles behind their internal benchmarks?
They had a few key goals. One, focus on measuring core capabilities, reasoning, perception, not just whether the output looks right superficially. Two, cover both atomic skills like OCR accuracy and integrated capabilities like solving a complex visual puzzle that requires multiple steps. Three, and this is really interesting, use LLMs as judges.
Using an LLM to evaluate another VLM's output. How does that work reliably?
They use carefully crafted prompts and provide the judging LLM with reference examples. The LLM evaluates the quality, correctness, and helpfulness of Seed 1.5-VL's responses, especially for open-ended complex tasks where a simple score is hard to define. They say they continuously refine these judging prompts to ensure accuracy.
A more nuanced evaluation for complex tasks.
Exactly. They also work hard to prevent benchmark overfitting, carefully deduplicating data, refreshing tasks periodically, and they ensure diversity in tasks and inputs, including a specific category for out of distribution tasks, things the model definitely didn't see in training.
Testing true generalization. Smart. So how did it do overall?
Pretty impressive. On the public benchmarks, it achieves state-of-the-art results on quite a few, including Math Vista, several tough visual reasoning benchmarks like VLM and checking if VLMs are blind, plus video tasks involving time and streaming. It also did really well as a GEI agent in games like 2048 Table 6, shows some scores there.
Solid performance.
Very solid. On others, like the challenging MMNU benchmark, it was highly competitive. And importantly, on their own rigorous internal benchmark, designed to be harder, they showed it surpassed comparable leading models.
Oh, our listeners got something to share. Let's hear it. Absolutely. We're just getting to the really interesting part about how it performed against other top models and some of the more nuanced things it could do.
Exactly. We were about to mention how it stacked up against other leading models on their internal benchmarks and then dive into some specific examples of its capabilities.
Right. On their internal evaluations, Seed 1.5-VL actually outperformed models like Llama 4 Maverick.
And to your point about integrated out-of-distribution capabilities, the paper includes some fascinating qualitative examples that really showcase its strengths.
Tell us more about those.
One set of examples involves solving rebus puzzles, where you have to combine pictures and letters to figure out words or phrases. We're talking about things like images and the number 4, and then get it to mean forget it.
Oh, yeah, I know those. How did it do?
Remarkably well. Figures 7 and 8.3 in the paper show it correctly deciphering rebus puzzles for words like breakfast, potato, and travel the 7 seas. These aren't things it was explicitly trained on, so it shows a real ability to combine visual understanding with wordplay.
That's impressive. What other kinds of integrated tasks did it tackle?
Another great example was correcting poorly written Python code that was just drawn on a whiteboard, as shown in Figure 8.
That sounds tricky.
It requires accurately recognizing the handwritten code through OCR, understanding the structure of the code itself, and then identifying and correcting the bug. It's a multi-step reasoning process involving both visual and logical understanding.
Wow. So it's not just seeing, it's understanding and acting.
Precisely. And its performance as a GAI agent in games like 2048 also demonstrates this integrated capability. It has to perceive the game screen, plan its moves, and then execute them effectively.
So it sounds like it can really generalize its learned skills to new and complex situations.
Exactly. It seems like a significant step towards more general visual intelligence.
But even with all these advancements, what are some of the areas where it still faces challenges?
The paper is quite transparent about the limitations. One key area is really fine-grained visual perception. For instance, accurately counting a large number of small, irregularly shaped or partially hidden objects remains difficult.
Like trying to count grains of sand in a blurry photo?
Something like that, yes. Or distinguishing very subtle visual differences between objects that look very similar. It can also struggle with precisely understanding complex spatial relationships, especially when viewed from unusual angles. Sometimes it might miss tiny details or make errors in very precise localization.
So it's great at the high level stuff, but the finer details can still be tricky.
That's a good way to put it. Another challenge they point out is what they call complex combinatorial search.
What does that involve?
Figure 27 in the paper gives an example of a puzzle where you need to find numbers that meet specific criteria, like only using prime digits. Even though the total number of possibilities isn't enormous, systematically exploring and checking all those combinations still seems to be a hurdle for current VLMs, including this one.
So it's not about seeing or basic reasoning, but more about that systematic process of trying out different options.
Exactly. It suggests that current reasoning approaches might not be ideally suited for tasks that demand exploring many possibilities under a set of complex rules.
Interesting. So what do the researchers see as the next steps in this kind of work?
Given their scaling analysis, which suggests that performance hasn't plateaued yet, one clear direction is simply to scale up the model even further with more data and compute.
Bigger and better.
Precisely. They're also very interested in unifying these reasoning capabilities with image generation. Imagine a VLM that could not only analyze a diagram, but also generate intermediate visual steps as part of its reasoning process, or visually modify an image to solve a problem that could lead to what they call visual chain of thought.
Actually drawing out its thinking. That's a cool idea.
And finally, they see a lot of potential in integrating more robust tool use mechanisms. This would go beyond just interacting with graphical interfaces to having the model seamlessly utilize external tools like calculators, search engines, or knowledge bases to help it solve complex problems.
Okay, this has been an incredibly thorough overview. We've really dug into the details of this model.
Yes, we've covered a lot, from the unique architecture and the carefully designed multi-stage training process
To the massive and targeted data curation efforts for areas like STEM, GI, charts, and video, and how they tackled the long tail problem.
and the really innovative post-training techniques, including RL with verifiable rewards, and that fascinating idea of using the VLM itself as a reward model.
Not forgetting that iterative self-improvement loop, where the model learns from its own best verified outputs. It's a really sophisticated approach.
And the critical infrastructure innovations that make training these huge asymmetrical models even possible at scale.
Understanding these specific technical choices really gives you a much deeper appreciation for the progress being made in VLM research. It's like getting a behind-the-scenes look at how these powerful AI systems are being built.
Absolutely. The level of detail and the innovative solutions presented in this work are truly pushing the boundaries of the field.
So as we wrap up, it's clear that we're making huge strides in creating models that can see, understand, and reason about the visual world in increasingly sophisticated ways. But with remaining challenges like fine-grained perception and complex search, it makes you wonder what the next fundamental breakthrough will be to reach truly robust visual intelligence.
It's definitely one of the most exciting and actively researched areas in AI right now.
Thanks so much for joining us for this deep dive. We hope you found this exploration of Seed 1.5-VL insightful.
We really appreciate you tuning in and being a part of the conversation. Until next time.